just start off with the heat and temperature section of the syllabus. All right, so we finished the mechanics section. So we're just going to do the heat and temperature, which is a very short section. So I think today we can actually cover the entire section of section B. All right, so the first thing under heat and temperature is to differentiate between what is temperature and what is heat, right? So we know that temperature is how hot or cold something is, and it's dependent on the amount of heat energy that is present, right? So the link between temperature and heat is that when you have heat, it affects what the temperature value is. So if you have a high amount of heat, then that means your temperature is high. If you have a small amount of heat, then that means your temperature is low, right? And we know the instrument used to measure temperature is our thermometer, right? We know that the units that we use for temperature are degrees Celsius or Kelvin, right? So the thermodynamic unit of temperature is Kelvin, right? And that's the unit that we're going to use in all our calculations for this section, right? So let's now move to the gas laws, right? So we have 3 gas laws that we should actually know by heart. So let's go. What's the first one that we're going to look at? So what are the gas laws? The pressure law. All right, so one is the pressure law. Any other? The Charles law. And the final one would be Boyle's law. All right, so these are the 3 gas laws that exist. So these 3 laws actually tells us how gases behave under specific conditions. Now, the conditions that we use for these laws are P, B, and T, where P here represents the pressure, B represents the volume, and T represents our temperature. So these are the 3 quantities or variables that will be affected in each of these laws, right? So let's go with pressure law. So the thing though is that for each of these variables, there is one that is constant, right? So we have 3 laws, we have 3 variables. Each variable is constant only once, right? So in pressure law, our constant variable is volume. So in pressure law, volume remains constant, right? So if we have volume of the gas is constant, then if we have, so the volume is the same, right? So V1 equals V2. We have the gases, particles there. It's saying that if we increase temperature, so if temperature increases, then the pressure that the gases will exert will also increase, right? So for pressure law, if temperature increases, then the pressure that the gas particles exert will also increase. And that's because you're giving the particles more energy so they can move about and hit each other, so they create more pressure, right? So in that case, we know that for pressure law, the equation would be that P1 over T1 equals P2 over T2. So this here is the equation for the pressure law, right? So we notice that volume is not present in the equation because it is constant, right? So the volume of the container remains constant, then therefore once the temperature increases, then the pressure that the gases exert will also increase, right? Then we get that equation. All right, let's go to Charles' law. Now with Charles' law, then what is constant here is pressure, right? So in Charles' law, we have pressure being constant, right? And what it's saying is now the volume is not constant, but the pressure that these gases particles will exert will be the same, right? So in this case, if we increase the temperature, then that means our volume of the gas also increases. And that shows us that when we increase the temperature, they get more energy so they can actually spread more. So in spreading more, that increases the volume of the gas, right? And in that case, we have that the V1 over T1 is equal to V2 over T2, right? And we notice again that the pressure, the constant, is not present in our equation, right? And then finally, right, so we have used the P and V, so therefore in Boyle's law, temperature is constant, right? Now I can give you something to remember for Boyle's law, right? So when something boils, right, especially from chemistry knowledge, when something is boiling, the temperature is kept constant. So when water boils, changing from water to vapor, it actually stays at 100 degrees when the vapor is being formed. So that's a constant temperature. So boils, just like boil, we have at boiling, we have a constant temperature, right? So our temperature is constant, so therefore, what's the relationship now between P and V? So in this case, if we increase the pressure of the gas, then that means, or we increase the volume, sorry, of the gas, then the pressure will decrease, right? And in that case, we get the equation that P1 V1 is equal to P2 V2. So once the volume of the gas increases, then that means the pressure that they exert will decrease, right? Because now the space that the particles have to move gets bigger. So in the case where they're moving towards the boundary of the container, they're going to lose energy. So at the point of contact with the container, that energy that it has is very small. So the pressure it exerts on the wall will be small as well, right? So that's the reason why pressure and volume would be inversely proportional, right? So for pressure law, the volume is kept constant, right? And the pressure and the temperature are directly proportional. So when temperature increases, the volume increases. For Charles' law, pressure is constant. So when temperature increases, then the volume of the gas also increases. And in Boyle's law, temperature is constant. So when the volume of the gas increases, the pressure decreases. So they're inversely proportional, right? And we have our three equations for our three laws, right? Now we know that if we combine these equations, we get our general gas law equation, right? That says that P1 V1 over T1 is equal to P2 V2 over T2, right? So these four equations we'll be using to actually do some calculation in return in terms of the behavior of particles with these variables, pressure, volume, and temperature, right? So these are pressure laws, right? And we're going to do some questions when we finish with all the topics under this section, all right? Any questions for this part? All right, so now that we have been through the gas laws, we're going to look at our specific heat capacity and heat capacity. So heat capacity versus specific heat capacity. All right, so question, what's the difference between heat capacity and specific heat capacity? Well, both have change in temperature, so not exactly. Heat capacity is the amount of heat required to change the temperature of a substance by 1 degree. Alright, so someone gave the definition of heat capacity, which is the amount of energy required to change the temperature of a substance by 1 degree, right? So that's correct. So heat capacity, which is a capital C, is the amount of energy required to change by 1 degree. So we get that equation, right? So it's any amount of the substance, how much energy it takes to change it by 1 Kelvin. And we specify heat capacity, which is a common C, is the amount of heat energy required to change 1 kilogram of a substance by 1 Kelvin. So we notice the difference here is that this equation has a mass and heat capacity doesn't. So the difference is that specific heat capacity only concentrates with 1 kilogram, right? So that's why it's called specific. So any quantity in physics that says specific of anything, then it's only pertaining to 1 kilogram of that specific substance, right? So heat capacity is any amount that you have, while specific heat capacity is only concentrated with just 1 kilogram of that substance, right? So that's the main difference between heat capacity and specific heat capacity. The heat capacity is a capital C, specific heat capacity is common C. All right, if we put both together, we get that C is equal to mc. So heat capacity is equal to mass times specific heat capacity, right? And also we should note that the temperature that we use is in the unit of Kelvin, right? So we always have our units in Kelvin. So the unit of C, capital C here, is joule per Kelvin. And for common C, the unit is joule per kilogram per Kelvin. Right? So these things are important between both quantities. Now, in the lab, when we try to determine the specific heat capacity of substance, we have the easiest way is by using the mixture method, right? And that's where we heat a metal, or let's say we want to find the specific heat capacity of a metal, right? So we heat the metal to roughly close to boiling point, 100 degrees for water. So we heat it in water, and then we quickly transfer it over to a container, an insulating container that has a specific amount of water, right? And we add the metal to it, which will cause the water at room temperature to rise slightly, right? And based on that, we can calculate our specific heat capacity, right? So let's look at how we will generate the equation to calculate such. So we have the beaker with the metal inside that is boiling. So we apply heat to it from a Bunsen burner, right? We record the temperature, right? Then we transfer the metal into an insulating cup at room temperature, right? So we transfer the metal inside the water here. So in this case, this temperature will be your initial temperature, right? So let's say it's 100 degrees, right? Now, in this case, we have an initial temperature of room temperature, which is roughly, most times, 27 degrees. And after the metal it normally rises to something in the 30s, right? So that is unknown until you do the experiment. So we also would measure the mass of the metal and also the mass of the water. So the mass of the water in the cup will also measure that value as well. So in this case, we assume the big assumption here made is that the heat lost by the metal is equal to the heat gain by the water, and that's in this case. So the heat that this metal has when it's being transferred from the hot water, when it enters the room temperature water, it's going to lose heat. So we're saying that that amount of heat that is lost is actually the heat that is gained by this water to raise the temperature from 27 degrees to the temperature that you get, right? So in this case, the heat lost would be mc delta T, and that is from your metal, and it's gained by the water, which is same mc delta T, but this case is by the water. All right, so we add the mass of the metal. All right, we need to find this value here. So this is unknown. The change in temperature of the metal will be, the metal is moving from, let's say, 100 degrees to the final temperature here. So we minus these two, and we get the change in temperature for the metal, right? And then the mass of the water in the cup times the specific heat capacity of the cup, which C of water is 4,200 joules per Kelvin per Kelvin per kilogram, right? And then the change in temperature of the water will be from room temperature to the temperature that it will increase after the metal is placed in it. All right, so that's how we normally use to find the specific heat capacity of a substance in the lab. All right, is there any questions? All right, let me just repeat everything. All right, so when we heat the metal here, right, we normally heat it to close to 100. Then we transfer it quickly to the room temperature water in the cup, right? So in this case, it will cause this temperature to rise to a specific temperature, right? In that case, then we're saying that the heat that is lost by this metal when it's placed in the water will be equal to the heat gained by the water to change it from room temperature to a higher temperature. So this is the assumption that is always made, right? So the heat lost by the metal, remember that E is equal to mc delta T. So the heat lost by the metal is mc delta T of the metal, right? And it's gained by the water, which is the same mc delta T, but this time of the water. So we'll measure the mass of the metal that we use in the lab on a balance. We're finding the C of the metal, so it's unknown. The change in the temperature of the metal will be, it was originally at boiling point, right? And then it actually fell to this temperature that would record when we put the metal inside the room temperature water. And then over here we have the mass of the water, which is the mass of the water in the cup, times the C of water, which is 4,200, times the change in temperature of the water, which would be from the room temperature water to this water that it increased to. All right, so does that answer the question? All right, great. All right, so that's how we will find it. Now, in some cases, CXC will probably use the case of, instead of heating with a Bunsen burner, you heat it with a heater. So if you use a heater to measure, then the only thing that changes the heat that is lost by the metal, right? So in this case, we can use that P times T is equal to mc delta T. So in this case, instead of using the water, we're using just heating the metal, right? So we have the heat lost by the heater here, so this is your heater, is equal to the heat gained by the metal. So the heat lost by the heater is P times T, which can be found by Vt, P is equal to IV times T equal to mc delta T of your metal. Right? So if it's a heater that is used, then the equation simplifies to be in this. So we don't need water because we're just directly heating the metal to change temperature, and we can find the C right there. All right, that's clear. So we only use this equation when it's a heater that is used and not a Bunsen burner heating water with the metal. If it's a Bunsen burner that's heating the water in the metal, then we use the previous equation. If it's a heater that's directly heating our metal, then we use this equation. All right. So that is heat capacity. All right. Now let's look at, and as I said, we're going to look at some questions once we finish these topics. So this is a very short section of the syllabus. So once we finish with these topics, we're going to do some questions which involves the use of all these equations. All right. So the last part that we're going to look at is the latent heat. All right. So you have latent heat and you have specific latent heat. So remember, specific just means that we're just focusing on 1 kilogram of the substance. Latent heat would just mean it's any amount of the substance, right? So if heat capacity or specific heat capacity was to change the temperature by 1 Kelvin, what do you think that latent heat is? Yes, what do you think that latent heat involves? Latent heat, anything about latent heat?
Latent heat is the heat at which a substance changes from one state to another. The exact point at which it changes.
All right, great. So it's the amount of heat required to change state, right? So between solid, liquid, or gas, right? So we have the two types, which are fusion and vaporization. So what state would it change from to?
It changes from a solid to a liquid.
So from solid to liquid, and vaporization would be
From liquid to gas.
from liquid to gas. All right, so that's so specific latent heat of fusion is the heat required to change 1 kilogram of a solid to a liquid without a change in temperature. Right? So remember, once there's a change in your state, temperature always remains constant. So in this case, we have E is equal to mLF, where LF is your latent heat of fusion. And for vaporization, it's the heat that's required to change 1 kilogram of a liquid to gas without a change in its temperature. And this is also E is equal to mLV. Right? So these two are very important, right? You just need to remember what changes from fusion is between solid to liquid, and vaporization is between liquid to gas. Right? So that's both equations that we use for specific latent heat. So we use these equations. If you notice, there is no temperature there because the temperature is constant, right? So once a question has a constant temperature, then we are going to look at latent heat, right? So, and also if it has a change of state, then it's latent heat. If there is a change in temperature, then it will be heat capacity or specific heat capacity, right? So that's very important to distinguish between latent heat and heat capacity. So once there is a change in temperature, it is definitely heat capacity. But once you have a change in state or a constant temperature, then it's latent heat. All right, so that's very important for us to remember when we're going to do calculations. All right, so this session is going to finish. All right, so I'm going to restart and then we go to some questions. All right, so we're going to restart and look at some questions to involve all the things that we have done so far. All right, so let's go to some questions now. All right, so first question here. Answer the following questions using the kinetic theory of matter. Explain why thermal energy has to be supplied to a liquid at its boiling point to be changed into a gas without any change in temperature. and why the volume of the gas produced is much greater than the original volume of the liquid. All right, so anyone wants to try that? Why do we need heat in order to change from a liquid to a gas?
Can I try?
Go ahead, yes.
We need heat to convert from a liquid to a gas because when a substance is in a certain state, in order for the molecules to extend apart from each other, it needs more kinetic energy, and kinetic energy is given to it in the form of heat.
All right, great. So that's the exact answer there. So heat, you apply heat to the particles to get them further apart to break the bonds. So because between liquid to a gas, the gas particles are further away. So the only way we could attain that is if we apply heat to break those bonds so they can get further apart. So the second part of the question, why is the gas volume greater than the liquid volume?
Peter?
Why is the gas volume? So if you have a specific amount of liquid and you cause it to vaporize, why does the gas volume increase more than the volume of the liquid original?
Oh, because as expansion occurs, the amount of space required, increases as well. While as the spacing between the molecules decreases, the amount of volume required decreases as well.
All right,
It's
so
like, for example, like if I had like 8 fish and they were all stuck in a small jar, and then when I let them out into the ocean, they are able to spread apart further because they have more space.
I agree. So the heat that breaks the bonds between the liquid to change it to gas. So the gas now have more space to work, has more space between the particles, so it cause a greater volume in its capacity. All right, next part, state the energy change that occurs during the phase change from liquid to gas. And what is the name of that energy change?
Vaporization?
Vaporization. All right, so the next part, a gas exerts a pressure on the wall of its container. What causes this pressure?
Repeat that one, sir.
So gases exerts pressure on the walls of its container. What causes this pressure?
Oh, due to the amount of space between the molecules, in order for them to keep that space, a constant spacing and a certain volume or a certain amount of space given, they need to exert force on the walls of the chamber in order to keep their spacing as far apart as possible. Or they'd revert back to their other state.
All right. All right, so the answer is there, yes. All right, so it's because they're in random motion. Remember, particles are always in random motion. So they have energy. So once that energy hits, they have that energy, they hit the wall, then that produces the pressure. Because remember, pressure is force over area. So once you have energy and you're moving, so that means there's a force, and then when you hit the container over that specific area, it produces pressure. All right. Let's go to part B now. At standard temperature and pressure, that is 0 degrees and 1.01 times 10 to the 5th Pascal pressure, the density of oxygen is 1.43 kilogram per cubic meter. Oxygen is stored in a container of volume 3.87 meter cube and a pressure of 2.02 times 10 to the 5th Pascal at a temperature of 25 degrees Celsius. What volume would So what volume would the same mass of oxygen occupy at standard temperature and pressure? Calculate the mass of oxygen in the container.
I don't know yet. I'll work tomorrow, but the boss will come and answer. I'll tell me I'll come out tomorrow. I'll see.
All right, so the first part here is to calculate the volume of the same mass of oxygen occupied at standard temperature and pressure. All right, so let's write what we have. So we have at standard temperature and pressure, that's T1, it's 0 degrees.
Yeah.
We have
Close the
P1,
door.
which is the pressure. which is 1.01 times 10 to the 5th Pascal. All right. We don't need the density as yet. All right. And we're given that the volume of oxygen is 3.87 meter cube. And at this same pressure, it is 2.02 times 10 to the 5th Pascal. And it's given that the temperature is 25 degrees Celsius. And the first part here is to find the volume at room temperature and pressure. All right, so we notice first of all that this is deal with gases. So we have to look back in our gas laws, right? So remember we had 3 laws and 4 equations. All right, so the first part is to check, is there any change? Is there anything that is constant first? So is there a pressure that's constant, a volume that's constant, or a temperature that's constant? And based on the question, is there any constant between those variables?
Yes, sir. Standard temperature and pressure. Both of them are constant.
No. All right. So constant meaning that they did not change between the initials part and the second part of the question. So these are 2 and these are the 1s. So the 1s here and the 2s here. So if it's constant, then that means whatever it was at 1 is the same thing at 2. Right? So it did not change any value throughout this duration.
Then the density is constant.
No, we're not looking at density as yet because we don't need density to calculate. Let's see, the density. So we have the density here. We don't have so we are not able to use density as yet. Right? So we notice that everything changes. So the pressure, the temperature changes between 0 and 25. The pressure changes, right? So therefore, and also it asks him to find the volume, so that means volume also will change. So that means we are not able to use Strauss law or Boyle's law or the pressure law. So the only equation would be our general gas law, right? So that includes everything that we have.
So why are we only using the general gas law though?
Because none of these quantities are constant, right? So we notice the temperature change between 0 to 25. The pressure changes from 1.01 to 10 times 10 to the 5th to 2.02 times 10 to the 5th. Right? And we're asked to find the volume when we have a 3.87 meter cube volume. So nothing is constant. Everything changes.
Yeah, I see it now.
Right? So all we're doing now is to substitute our values here. All right, before we substitute, remember our temperature needs to be in Kelvin. So that means we add 273 to each. So we get 273 Kelvin for T1. And this would be plus 273, which gives us 298. Right, so we substitute our P1, which is 1.01 times 10 to the 5th, times the volume V1, which is unknown, over T1 in Kelvin, which is 273, equal P2, 2.02 times 10 to the 5th, times V2, which is 3.87, over T2, which is 298. All right, so when we calculate that, we're supposed to get, all right, so this side here, the right side, we get 2623.29, right? If we divide these two, we get 369.96 V1. So we divide by 369.96 on both sides. So therefore, volume 1 would be 7.09 meter cube. All right, is that clear? So that would be the volume of the gas at standard temperature and pressure. All right, and then the next part says calculate the mass of oxygen in this container. So we need to calculate the mass. All right, so it gives us the pressure. So the density of the gas at this volume. So now we can find the mass, right? Because we know that density is equal to mass over volume. So density is equal to mass over volume. So mass is equal to density times volume. The density is 1.43 and the volume is 7.09. And we get 10.14 kilograms. All right, so now let's look at this question. So it says a C-Sec physics teacher gave two groups of the 1.43 was from the question. Here, they gave it in the question. So it said the density of oxygen is 1.43 kilogram per cubic meter. All right. All right, so this one, a CXC physics teacher gave two group of students project on specific heat capacity. Group 1 used an electrical method to calculate the specific heat capacity of a metal block. The circuit used in this method is shown in figure 3. All right, so describe the method used by this group to determine the specific heat capacity of the metal block. All right, so based on that, we should be able to generate a method, right? So that should be good. The second group of students determined the specific heat capacity of a liquid. One set of results is obtained below. So it took 300 seconds for the temperature of 0.1 kilogram of the liquid to be elevated from 25 degrees Celsius to 50 degrees Celsius. The energy supplied was 13.6 kilojoules during this period. Assuming that no heat was lost and ignore the heat capacity of the container, determine the value of the heat capacity of the liquid. All right, so again, we're going to identify what we're given in this case. So we're given the time it took, which is 300 seconds. Right, we're given the mass, which is 0.1 kilogram. We're given the initial temperature, which is 25 degrees, and it moved final temperature to 50 degrees. Right, and then the energy supplied is 13.6 kilojoule, and we need to find the C of the liquid. Alright, so this is the mass of the liquid. Alright, so it says assuming no heat was lost, then that means the heat lost by heater is equal to heat gain by liquid. Right, so that's our assumption that we will make. So the heat lost by the heater is given, so we don't have to work that out, which is 13.6 times 10 to the 3, because it's kilojoule. That's equal to MC delta T of your liquid, right? So the mass of the liquid is 0.1, the C of the liquid is unknown. The change in temperature would be minus the 50 and the 25, so we get 25 there. All right, so we get 2.5 C, 13.6 times 10 to the 3, divided by 2.5 on both sides. So we get C to be, so we get 5,440 joule per kilogram per Kelvin. All right, any questions from this? All right, so let's move on to the next one.
The L.
What's
The L.
for the liquid. So we're finding the C of the liquid. So the mass of the liquid and the C of the liquid.
Oh, okay.
All right, so the next part says if the liquid was heated twice as long, what impact, if any, would it have on the specific heat capacity of the liquid? So it's saying that if we had heated this instead of 300, it was twice, which is 600 seconds, would it affect this value that we have calculated? Anyone wants to attempt that? If we increase the time of heating it, would it affect the answer we got?
Repeat, sir.
It's saying that if we increase the time to twice this amount, 300 to twice it, so it's 600, would it affect the answer that we got for the heat
No,
capacity
sir.
of the liquid? What's that?
No, sir. No, it'll remain constant.
It would remain constant, right? So if we change the time, the same value will still be received. Now, why would that be the case?
Because with the time being increased, even though the mass will remain constant, the temperature would also increase by doubling. It also be doubled. The temperature increase would also double.
Great. So if you increase the time, then that means your final temperature will also increase as well. So that variable of increase will still cause us to have the same value of C. Right? So that means this value now would increase by twice the amount, right? So, and remember, the C of a substance is a constant value. So it doesn't matter if you heat it for a longer period of time or a shorter period of time. Once you have this amount of energy there present, then it's going to change the temperature, right? So that's the key part. All right, so that's it for this question here. All right, so let's look. All right, so there is a latent heat one now. All right, so we're looking at part B that says a physics student was provided with 25 grams of ice to convert to steam. All right, so we're moving from ice to steam. How much heat is needed to change this 25 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius? All right, and we're given those constants there. So the specific heat capacity of ice, we're given the specific heat capacity of water, given the heat capacity of vaporization, and the fusion. All right, so we're moving from ice. All right, but before we can move to ice to gas finally, we have to go through our liquid stage, right? So we move from ice to liquid and from liquid to finally to gas. All right, so that's important. We cannot ignore our liquid stage, right? So in this case, we have the heat lost equal heat gain, which is always an assumption, right? So the first thing is that our temperature of the ice will change, right? So the ice, so we have a change in temperature of the ice before it starts to melt. So that means it's MC delta T of the ice, right? And then when it starts to melt, it's going to change to a liquid, so that's MLF. So there is no change in temperature, right? Plus, it's now going to change temperature in order for it to start going to gas, right? And then we have it changing to a gas. So this is for water, right? So we have the change in the supply, the heat supplied is to change the temperature of the ice for it to start melting, right? The ice melts to liquid or water, and that temperature has to now change to reach to 100 degrees before it starts to vaporize. So do we understand this equation before we move on? Yes, do we understand this before I take it?
Sir.
All right. So now we substitute our values. So the mass of the ice is 25 grams, so we change it to kilograms, is 0.025 times the C of the ice, which is 2 times 10 to the 3 times the change in temperature of the ice. All right, so the ice is moving from 0 to room temperature, which is 27. All right, so it will start melt at 27. So this here is our heat loss, right? Then it's gain, so it's the mass. So it's the same mass, 0.025 times our latent heat of fusion, which is 3.4 times 10 to the fifth, right? So that is when it's changed into a liquid, plus now when it's changing temperature as a liquid, which is the mass, 0.2025, times C of the of water, which is 4.2 times 10 to the 3, which is 4,200, times the change in temperature, which is from room temperature to 100 degrees for it to start turning to a steam. And that is 73 difference, right? And then finally, plus when it's changed into a gas now, which is mass times latent heat of vaporization. All right, sorry, this here, sorry, this is plus, so this is what we're finding. Sorry about that. And vaporization here is 2.3 times 10 to the, all right? So we're finding the heat that is lost to change it from ice, change the temperature of ice to start to melt, which change it from water temperature to start to get it to steam. All right, so if we do all this calculation, all right, let me see if I can put everything in the calculator one time.
Sir, I have a
Yes.
question.
Mm-hmm.
So whenever they ask us to see how much energy is required to convert from ice to water, for example,
Mm-hmm.
we'll have to do the heat capacity, the specific heat capacity of ice, plus the latent heat of fusion, plus the specific capacity of water to get the total amount of energy required.
Yes.
All right, sir.
Sure. All right, so when we do everything here, we get that E is 75015 joule. All right, so that's the amount of energy that will be needed to change from ice to gas of 25 grams of ice. All right, so again, just to review, we have ice temperature changing before it starts to melt, then it starts to melt. All right, so we have water now, so the water temperature changes before it starts to turn to steam. All right, so is that clear for everyone?
Yes, sir.
All right, great. All right, so that's basically all the calculations that you need to actually work with this section of the syllabus. All right, so it's the same process over and over once you identify, but see in the last 2 years, I've actually gotten simpler than these, right? So I've seen where they have broken it down to help you guys. So I think last year paper they asked, this was something similar, but they've broken it down. So they asked what was the energy that's required to change from ice to liquid at one part of a question. And they asked what was the energy required to change from liquid to gas, and that was the next part of the question. And then they asked what's the total energy, which would be just adding both, right? So basically the last time they did it was to break up the questions into parts to get the final answer. Right, so they can give you in parts as well as they can just give you in one set to find the final answer. All right, so that's the use of our gas laws and heat capacity and specific heat capacity for this section. So the last thing under this section of the syllabus is to talk about absorption of heat, emission of heat, and reflection of heat. So we know emission of heat means that these objects produces heat. Absorption means that they take in heat that is incident to it, and reflectors mean that they bounce off heat that is incident onto it. So materials that are good absorbers of heat are normally dark colored objects. So black or any dark colored objects, right? So those are good absorbers of heat. Shiny objects are normally good reflectors of heat, right? Bright color objects are good reflectors of heat as well, right? So that's the reason why if you are in a dark color object, especially in the summer, you feel way hotter than if you were in a lighter color, right? Same thing applies if it's in the winter time. If you are in a darker color, you feel more warm than if you're in a lighter color because dark objects absorbs the heat, right? While the bright colored objects, they reflect heat. And that's the main reason why the firefighter uniform is actually brighter colored and it's shiny, right? So if you notice the color of the firefighter uniform, it's brightly colored and it's shiny when you look at it because these uniforms need to ensure that it can maximize on reflecting the heat away from the firefighter, right? So it uses bright colors to enhance that reflection as well as it's very shiny. And you notice that it's not fitted onto the person, it's a bigger area, right? So it's way big, so that means that it increases the ability to reflect heat away from the person that is in it. All right, so that's clear for everyone.
Yes, sir.
All right.
So
Mm-hmm.
um so is there like a mathematical equation that could tell us the absorbability or the ability of a material to absorb or release heat?
Yes, there is, but it's not at this level. That's until you reach unit one of K. So it gives you an equation that tells you how much heat can be absorbed by a body based on how thick it is and the type of material that it's made of, right? So those things, those persons, those manufacturers of especially the firefighting uniforms have to take these things into consideration, right? Because heat, it, it, these objects, bright colors do reflect, but they actually will absorb a certain amount as well. So you need to ensure your calculation will match up to ensure that it maximizes on the reflection rather than the absorption rate. All right, any other question? All right, and the final thing is the methods of heat transfer. So you know we have three types of methods in which heat is transferred from one to the next, and those three methods are, yes, what are those three methods?
Conduction, convection, and radiation.
Conduction, convection, and radiation. Right, so we know conduction has to do with the objects touching, right? So just as when you're cooking, the only way heat can transfer from the pot to your hand based on conduction is if you touch it. So once you touch it, you feel that heat because of conduction. So the heat transfers from where it is high to your body, right? Now, convection deals with the upward or downward motion in a fluid. And fluid in physics is either gas or liquid. So it's not just liquid. So it's also in gas state, but it's the motion is either up or down, right? So convection cannot actually go to the side. So it's an up or down motion of heat. So example, when you're cooking, right, you notice that the bottom of the pot gets hot first, and then it starts to produce some little bubbles that will start to rise to the top of your liquid. That bubble rising is because the heat is being transferred upwards in your liquid, so the entire liquid can be hot as well, right? So that's a convection. And then radiation method of heat transfer is where there is no need for any medium, right? So we don't can happen in empty space, in a vacuum, right? So that's the reason why we can feel the heat from the sun that passes through space where there is no air particles, no medium for anything to travel. So it travels through that space and reaches us here on Earth so we can feel the warmth of the sun, right? So that's a form of radiation. It doesn't regards the direction. So it can be the sides up or down vertically. It doesn't matter of the direction. But so those are the three types of heat transfers, that heat is transferred from one to a next. All right, so we're going to take this time to do some questions, some past papers, 3 past papers, and then we can finish for today since we're finished with this section. All right, so remember most of the first questions we would already have gone through. We have done this first part already, so we're going to skip over these questions to where we would start, which is question 15. All right, so question 15, we'll start from here. All right, so it says the specific latent heat of vaporization of water is the energy required to change 1 kilogram of water at, what would be the answer here? C? Yes, great, C. I am not sure why you're not hearing. Everybody else is hearing me?
Yes, sir.
All right, so please check something on your side. All right, so C here would be the answer because there is no change in temperature, right? So so it couldn't be 0 because, couldn't be A because for liquid to change to vapor, then it has to be 100, right? And not 0. All right, 16, which of the following is the poorest conductor of thermal energy? Air, copper, mercury, aluminum.
A.
Air.
Yes, sir.
Any other answer? Yep, so it is air because everything else are metal characteristics, which are very good conductors of heat. All right, next, which of the following best describes or illustrates convection current in a liquid? C. All right, someone says C, someone says B. Any other? B. Yes, it is B. Right, so it goes up and then circulates to downwards. So up, then down. Right, so B. R18, Boyle's law for a gas can be tested experimentally, provided which of the following remains constant. So remember in Boyle's law, which one is constant? Yes, and a B. Someone saying B. All right, yes, it is B. All right, so it's Boyle's law. Remember anything boiling, constant temperature. So constant temperature and all these laws, the mass of the gas is also kept constant. So it's 1 and 3, which is B. All right, 19. The specific latent heat of fusion of water is 340 kilojoule per kilogram. This means that when 10 kilogram of water freezes, then what happens? So remember, fusion is from solid to liquid. So between solid to liquid, would you need to absorb heat or give off heat? All right, someone says C. D. Someone says D. All right, so I think the answer is between C or D. All right, someone is saying A. All right, so the question now, let's differentiate. The question would be, would heat be absorbed to change from solid to liquid or be given off? So from solid to liquid, it will be absorbed, right? So that means it eliminates B or D, right? So we have to absorb heat for it to change from solid to a liquid. So let's see now. So remember that E is equal to MLF, right? And we need to know how much this is. So we're multiplying the mass times LF. So we multiply 10 by 340 kilojoules, so we get 3,400 kilojoules. All right, so therefore our answer would be C, because we're multiplying to get the energy. So it's not A. A would mean that you divide it, but we're not dividing, we're multiplying to get E. Because E is equal to MLF. All right, 20. As the temperature of a liquid rises, what changes? C, the kinetic energy of its molecules increases. Great, so that is correct. Remember, increase in temperature would cause them to get more energy, so they will start moving faster. Moving faster would mean that your kinetic energy increases. All right, 21. The specific heat capacity of a material is the energy required to. So you have specific there, so that means you have to have 1 kilogram there in your answer. Right, so that eliminates B as an answer there. So someone says D, to change the temperature of 1 kilogram of material by 1 Kelvin. D, great. All right, 22. What is the gain in gravitational potential energy of a body of weight 200 Newton as it rises from a height 30 meters to a height of 35 meters from the Earth's surface? All right, so this is, we know that gravitational potential energy PE is equal to mgh, or delta H in this case. So the mass is, so mg there is 200 times the change in height, which is 5. So 5 times 200 is 1000. So we have C for our answer. All right, next, 23. Which of the following statement concerning the radiation of heat is or are true? Radiation can only take place in a material medium. A good absorber is also a good emitter of radiation. Dark, dull surfaces are better emitters than shiny ones. All right, so which one of those statements are true? D, so 2 and 3.
Richard, please go up for a quick second, sir.
Which question, 22?
Yes,
C.
sir. All right, sir, you can move on.
Okay. All right, so 23. So we know that the first statement is wrong, because radiation can happen in empty space. So that eliminates B and C. So we know that 3 is correct, right? So we need to differentiate if 2 is correct. So a good absorber is also a good emitter of radiation, and that is also true, right? So that means it's 2 and 3, which is D, as you said. All right, 24. An electric kettle full of water is plugged into the mains. The process by which heat travels through the water is called
B, convection.
B, convection. Great, because it's liquid, so that is convection. All right, there are 25. There are little or no attraction forces between the molecules in a
In a gas.
gas. All right, next, 26. What temperature is indicated by the clinical thermometer in the diagram above? All right, so let's see. So we have A, 38.3. No, it's, all right, let's,
D.
D. All right, so this right here, this stroke right here, that is 38. So this is 38.5, and it's 3 away, so 38.8. So it's D as in. All right, so that's it for this section that we have just completed. All right, so let's go to our next paper. All right, so again, these questions we have been through. All right, so now we have some new ones here. So let's start at question 9. All right, so it says item 9 refers to the following diagrams which depict some simple machines. In which of these machines would the effort applied be less than the load? So which one shows that
That'd
effort?
be 2.
What's 2?
Yes, sir.
Only 2?
Oh,
All right,
wait, no,
there's
no, no. Wait. No, wait. What would that be? 1, I mean. 1 and 3.
1 and 3.
1 and 3.
No, it's actually 1 and 2.
Oh, so 2 was correct.
Yes, 2 is correct. All right, so the
Oh,
answer
got
given
it now.
would be 1 and 2. So that's A. All right, so that, let me give you the reason why. So we have 3 classes of simple machines, right? Now, because if you notice 1 and 3, where the fulcrum is, right? The fulcrum is actually at the part where you're applying your 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 effort, right? And that's the reason why it needs less effort to actually apply those for those loads, because where the fulcrum is, that's where you apply your effort. So
So wait,
that's
sir.
9. Yes.
So you're saying that we apply the effort here? Is that the fulcrum you're talking about?
Yes, because if you use the tweezers, remember you normally put your fingers close up to that section, right?
Yes, sir.
And then for the nutcracker, your hands go right down to that groove right there.
So then it'd be less because of the
So it's
because of momentum, Newton meter, I
the
guess.
the moments,
Yeah, the moment I meant, yeah.
yes,
Moment.
because they're reducing the distance between the fulcrum and where the effort is.
Yes, sir.
All right,
Requiring less force because the distance is increased.
that is correct. All right, so next, a scalar quantity has
Scalar quantity has magnitude only. A.
magnitude only, so that's A. All right, 11. Body initially moving at a constant speed is brought to rest at a uniform rate, which of the following speed time graphs indicates the motion of this object. So it's moving initially at a constant speed, is brought to rest at a uniform rate. So which one shows that?
C.
A,
C.
C. Yes, it is C. All right, so C shows that this point it's constant, and then uniform deceleration we see going down. Right, so remember the straight lines show uniform. Right, so it couldn't be A because we have a curve coming down, so that shows us that is not uniform. All right, 12. Yes, we have done 12 before, so we can skip that. We also did 13, these already, so let's go to the section for heat. So let me just double check one thing to ensure this is a CSEC paper, because I've seen some things here. Yes, it is. All right, I'll go back. All right, so we're going to start at question 20. So absolute zero is the temperature at which, anyone knows what absolute zero is?
Absolute zero is like 0 Kelvin, which is negative 273 degrees Celsius.
Yes. So what is,
So what is what, sir? Oh,
so what does that temperature tells us?
that hmm, that'd be B.
I know it's C.
C.
Yes. So what absolute zero is, it's actually the lowest temperature a
Possible.
substance can attain, right? And if it's the
Yes, sir.
lowest temperature it can attain, then that means then it will not actually change its volume. So if you pass that temperature, there is no change in the volume of the object because it only can get to that low.
So then, technically it'd be like, in a sense, like like if you have a graph, it'd be like an origin point on the graph, where it has no length, width, or depth.
Yeah, basically, right? So anything below that's less than that value theoretically does not exist,
Oh, that's cool.
right? All
Yeah,
right, so
that's cool.
next, a pressure of a fixed mass of gas is P and its volume is V. What is the new volume if the pressure is increased to 2P
Wait,
at
sir, can you scroll up so I could get so I could print screen, like
what's
so I
that?
could, I want to like take a screenshot of that.
Okay,
All right, so you can move on now.
all right. All right, so if we have constant temperature, so constant temperature means whose law is that? So constant temperature signifies that's Boyle's law, right? So constant temperature, Boyle's law. So that means PV1 equals PV2,
Two.
right? So it says that if what is the new volume of if the pressure is twice. So if we twice the pressure, what would be this volume?
A. No, it'd be yeah,
So
it'd
we
be A.
all right. So
It'd be
let's make V2 the subject. So we get P1 V1 over P2, and we're saying that we twice the volume, the pressure. Sorry. So that means V2 would be a half of V, right?
yes, sir.
So that is A. Because basically these P would be the same, so we cancel. So we left back with V1 over 2. Right? Second, 22. The heat capacity of a body depends on. All right, this is 2008, the 2008 paper. Yes, what would be the answer for this one? The heat capacity depends on
Would it be C?
C? No, it's not
No, it wouldn't
C.
be C. Nah, it wouldn't be C.
All right, so let me help you out. Which equation you can use? So the equation that these questions are based on is that heat capacity is equal to M specific heat capacity.
Yeah, so it couldn't be A or B.
Which one?
No, I'm saying it couldn't be A or B, because specific heat capacity is the joules per Kelvin.
Yes, and it actually is E. Because if we notice this equation here, so your heat capacity is equal to your mass times your specific heat capacity,
Oh, yeah, I see it
right?
now.
So it's dependent on your mass and your specific heat
Specific.
capacity. So in this case, it's A, right?
Yes, sir.
Okay. So if it's dependent on, the first thing you do is to use your equations. So you only had two equations. It's either this one or C is equal to E over delta T. So it would be dependent on energy and change in temperature, right? And there is nothing there that has that energy and change in temperature, so it will have to be this equation. All
That
right,
makes
so
sense.
yes,
Nothing that makes sense.
okay. All right, next 23. Some molten naphthalene at 100 degrees is allowed to cool down to room temperature. The
If
naphthalene has a melting point of 80 degrees Celsius. Which of the following best represents the cooling curve of naphthalene? So which one represents the cooling curve of
C,
naphthalene here? Which one?
C.
A,
No, C.
C. Great. All right, so we know cooling curves. has a constant value here, which shows a change constant temperature there when it's changing from one state to the next. And that's the only one that has that. So it would be C.
Could you scroll up so I can see the top of the question? I wanted to screenshot that top part. All right, sir, you can move on now.
All right. All right, 24. The specific latent heat of vaporization of water is the energy required to change 1 kilogram of water, which we did this already, which would be C. All right. 25. Which of the following are reasons why a hot liquid placed in a double-walled vacuum flask retains its heat for a long time? 1. Evacuated space between the double walls reduces the loss of heat by conduction. 2. The silver lining walls reduce the loss of heat by radiation. 3. The silver outer wall helps to absorb heat from the surrounding.
Is it D?
All right, so let's see. So first, all right, someone is saying A, let's see. So
It could
point
be
one
D.
says the evacuated space between the double wall reduces the loss of heat by conduction, which is true, right? So the two walls are not touching, so therefore there is basically empty space there. So we can't have heat being transferred by conduction because they're not touching. So that's true. So 1 is a true statement. Then 2, the silver inner wall reduces the loss of heat by radiation. And 3, the silver outer wall helps to absorb heat from the surrounding. So if it's a silver outer wall, so it will absorb heat, right? Because it's shiny. All right, so 3 is correct as well. So 1 and 3 is correct. So let's see if 2 is correct. So silver inner wall reduces the loss of heat by radiation. Remember, radiation is where the heat is transferred through empty space. All right, so in that case, the
D?
problem with that is that it can be true and it can be false.
Which one, sir? Number 2?
Point 2, yes, it can be a true statement and it can be a false statement as well.
Why is that so, sir?
All right, so it does. So all right, so when the outer wall absorbs the heat, right? It wants to actually trap the heat inside the vacuum, so it keeps your liquid at a warm temperature. So that means it does not reduce it, but it actually enhances it, right? So it does not reduce it, but it enhances. So we're going to use that scenario. So therefore, it's only 1 and 3 which will be correct, which is B.
So wait, so you're saying that because silver allows the radiation to enhance the amount of heat being absorbed by the container,
Yes,
the vacuum flask. Thus, 2 is wrong because it actually enhances
that's correct.
it enhances the gain of heat.
Yes, so it enhances the gain of heat.
Yes, sir.
So it
So wouldn't that
doesn't.
be the same thing as saying reduce the loss of heat?
Oh yes, oh yes, that is true. So it's actually the next way. So it's 1, 2, and 3. So it's D. So let me remove this. So D. All right, 26. In which of the following is conduction the main method of energy transfer? Food heated in a microwave oven, energy transferred from sun to earth, food being cooked on a barbecue, food being cooked in a pot on an electric stove. So
D.
which one?
C.
C? Yes,
Yes, sir.
that's correct. Because the food is touching your barbecue grill, so that is conduction mainly.
And sir, not only that, that's not the only reason I said C.
What other reasons do you have?
Well, I was saying C because when you think of D, when you cook food in a pot, usually the pot is oil, and oil is a liquid which uses convection.
Mm-hmm.
So then B C because the food is straight on the metal, while in D, even though the electric stove does conduction straight to the pot, and if there's no oil in the pot, hypothetically, it would be conduction straight to the food. We all know that we need to put oil in the pot to cook food, so then it'd be convection and conduction for D. So it had to be C.
All right, no problem. Great. All right, so we have 7 minutes, so we should be able to do the other one because it's finished now. The next question is a wave question. So let's look at the last set, and then that's all right. So we're going to look at 2007. All right, so again, we've done those questions before. All right, so we can start at question 19. Which of the following best explains Brownian motion of smoke particles in air?
D.
The air particles are moving and colliding with smoke particles. Yes, so that is E. All right, so D is our answer for that one. All right, 20. In the pressure law, which of the following would be true? The ratio of pressure to Kelvin temperature is constant, the volume is constant, pressure is constant. So in pressure law, which one is constant? So remembering boys, law temperature is
Oh, the
constant.
volume is constant. The
So
volume is constant.
boys law is temperature. So in pressure law, the volume is constant. Right? So volume constant in pressure law. So that means P over T is equal to a constant. Let's call it K. So the ratio of pressure, yes?
90 is D, right?
So no, so the answer would be C. Right? So the ratio of pressure and temperature is a constant, so one is correct. And then two, volume is constant, which we know, yes, is correct. So it's 1 and 2, which is C.
No, sir, I was asking not for 20, for 19. 19 was D, right?
19, yes, D.
All right, sir.
All right, so 20 would be C, so 1 and 2 is correct. All right, 21, we did this already, so it is B as in boy. All right, 22. In a thermocouple thermometer, which thermometric property is used? Variation of electric resistance, expansion of metal, emission of electrons from a hot metal surface, production of current at the junction of unlike metals. What's that?
B.
B?
Yes, sir.
Yes, it is B, the expansion of metals. All right, 23. A gas is much easier to compress than a solid or liquid because the gas molecules,
C.
C,
Yes, sir.
moving very rapidly. No, not in
It
this
wouldn't really be
case.
that. It'll probably be B then.
D,
D.
But
right?
then they do force.
So they have no forces between, little or no force between them. So that means when you're compressing it, there is no resistive force to get it to be compressed.
Yes, sir, in a sense, D is technically erroneous. Because they said it has no force between them, even though they have force between them.
Well, because you have some books that will say it has small or no force, right? So it's, if you choose small force or no force, then CXC will accept any, right?
Oh, okay.
So small or no force, anyone they will accept. So D as in dog. All right, 24. Which of the following would be the unit of heat capacity?
B.
B, joule per kilogram.
Sorry, I meant C. Sorry.
C, yeah, so
C.
C is the answer. Remember, heat capacity, there is no mass. So therefore it's joule per Kelvin. So C. All right, 25. Which of the following is true of evaporation?
B.
B.
Yes, sir.
It occurs at the surface of a liquid at no definite temperature, and that is correct. So B as in boy. All right, 27. The figure above shows a piece of ice wrapped in copper gauze and submerged in a glass test tube of water. The water, when heated at the top, boils long before the ice is melted. The main reason for this is that someone says A, the test tube is a poor conductor of heat.
I don't think it would it be A, because aren't test tubes kind of good? I mean, not the best, but I wouldn't call them poor.
So no, but you have to pay attention to the other options as well. Right? So let's see. So B says copper is a good conductor of heat, say, which we know is true, but that's not the reason why the water boils before the ice starts to melt.
Yes, sir.
Right? So B cannot be the answer. C says ice is less dense than water, which has nothing to do with changing state and heat. So C is definitely out. And then D says water is a poor conductor of heat. So it's between. All right. So as I was saying that the water is a poor conductor of heat compared to test tube is a poor conductor of heat. So do we know water to be a good conductor of heat or poor? So in this case, water is a good conductor. So the only possible good answer here, the best appropriate answer would be A. So comparing the test tube conductivity to the water, the test tube would be a poor conductor than water. So therefore, A would be your answer. All right, so we will resume next class with some more multiple choice, as well as we'll be looking at the wave section of the syllabus. All right, so see you guys Wednesday.